start this recording. I realize that different Chem instructors, Chem 1 instructors emphasize different things. If a lot of the stuff is unfamiliar, then come see me during the office hours. I'll try to get you up to speed for the other stuff. Okay. But anyway, a lot of the stuff we aren't going to use all that much. And so the reason I'm doing this is just for repetition, so it doesn't fade from your memory completely.
Well, what happens if you forgot our Chem 1A?
What happens if what?
If you forgot the Chem 1A?
Then you should review it. If you covered it and just forgot it, just go back and review it. Some people say, oh, that means having to read, 1,000 pages. No, hopefully you have a note, you kept your notebook or something like that. You don't have to reread the book. Just, well, you don't have to review everything. What you want to review is, structure, because structure is important in chemical reactivity. So things that deal with structure, Lewis structures, this type of stuff. And so one of the things would be, do you know how to write the Lewis structure of an ionic compound? So many people mess this up. If I ask people to write the Lewis structure for calcium oxide, you know how many times I get this? All the time I get this structure. It's calcium oxide. It's totally wrong. It's not the structure of calcium oxide. They're trying to draw it as a molecular compound. Calcium oxide is not a molecular compound. Calcium oxide is a ionic compound. So so when I say review, you want to review things like how did they draw the structure, Lewis structure of an ionic compound? And you go back and flip back in the book and take a look. Take a look back in the book, and then you got it. And so the next reaction that we're going to do, actually this is the last one for that PowerPoint, is the calcium oxide solid. Now Lewis structures for ions are going to have these brackets around them. So that would be what's called a molecule of calcium oxide, or is that true? A molecule of calcium oxide? No. This is called an empirical unit or a formula unit. Empirical units or formula units. Formula unit is just the simplest empirical unit of this, because in calcium oxide we know that this is going to have some kind of crystal lattice like this, in which we're going to pack it together. It's going to be, I would say, since these are spherical ions, it should be something comparable to the sodium chloride lattice. Or something like that. It's not simple cubic. If you go back, simple cubic has a coordination number of 8. This one's actually going to have a coordination number much greater, because here we can each oxide is going to be surrounded by 4 calciums in the plane, plus 1 on top, 1 on the bottom. So it's actually going to have a coordination number 6. When we're thinking about simple cubic lattices would be a lattice consisting of all the same atom. And so we have simple cubic, we have body center cubic, we have face center cubic, it's all the same. But what the sodium chloride lattice is 2 interpenetrating face center cubic lattices. And so it would be a face center cubic lattice with all the octahedral holes filled with, well, sodium chloride is a face center cubic lattice of chlorides with all the octahedral holes filled with sodium ions. And so we looked at some simple salt structures like cesium chloride. Cesium chloride would be a simple cubic lattice with the cesium stuck right in the center of that, which we call a cubic hole. And then we looked at some others.
Out of curiosity, why is cesium chloride different configuration, different model than sodium chloride? They have the same electron.
Well, there's something called the radius ratio rule. And it has to do, the cubic holes are the biggest or the smallest of the holes in lattices. The biggest. Cesium ions are pretty big. And so octahedral or tetrahedral is too small for cesium. And so it just doesn't work. And so this radius ratio rule just takes the ratio of the size of the anion versus the cation and then sees, what's appropriate for that cation. And so in our class, what we did was we had a tiny tetrahedral hole where we took that tiny magenta, do you guys remember that? Pulled off a corner and stuck it in there. And that was a tiny tetrahedral hole. And then we built the sodium chloride lattice with the bigger blue balls. Blue balls fit in the octahedral hole. Did you guys do that? Yeah. That's it. And so this is the radius ratio. I would suspect something like a sodium chloride type lattice. From this. The oxides would form the FCC, and the calciums would be. That's just a guess, but we could see what it actually is. But we would have some kind of extended lattice like this. And one of these units, any of these, there's no fixed, like this calcium with this oxide is no different than this calcium with this oxide. So that's why we call them empirical unit. And this would be the solid. What is more reactive in a solid? A corner or a face ion?
Corner has three surfaces.
Yeah, a corner, because if you look at this corner, it's not bonded to as many things as a face. And so if there's going to be an attack on a solid, typically in the corners, like if you dissolve a sugar cube in water, the corners get attacked first, because then the rounds hit the corners, right? Or if your car is going to rust, it's going to rust where there's been some damage or some creases or defects introduced. So it's not going to be bonded easily. So I was looking for that. And so in general, surface ions are going to have higher free energy than what we call the interior. The interior are called bulk or interior. And this gives rise, like in water, it gives rise to surface tension, right? They're the same types of concepts, just interactions. Well, anyway, calcium oxide, is it soluble or insoluble? Calcium oxide is insoluble. Yeah. But it can be attacked by water, because when you think about oxide, oxide is a powerful base. But this oxide is different, because this oxide is not free. This oxide is locked in a lattice, so it isn't going to be as nearly as reactive, right, as sodium oxide. Sodium oxide is going to be a heck of a lot more reactive than calcium oxide. Solubility, interestingly, has some simple impacts. Calcium salts, obviously, this should be less reactive than sodium, right? Did I, in Chem 1A, remind me, did I talk about sodium versus calcium EDTA? Did I talk about that? Let me talk about that, because EDTA is something we're going to talk about in the next chapter. There are two, lead is, I guess, is lead, what's going on with Michigan, Flint, Michigan right now?
Oh, yeah, the lead piping roads.
Lead pipes, right. And so that leads to high lead levels, right, VLLs. And there's two therapies for, maybe there's more, but there's two medicines available for blood poisoning, lead poisoning. And what these are calcium EDTA and sodium EDTA. Now, EDTA is a very interesting ion, because what EDTA is, it's a powerful Lewis base, and it looks for ions to attack. It attacks these ions and just encapsulates them. renders them inert. And so what they're trying to do is they're trying to capture the lead in the blood using EDTA, forming an EDTA lead product, which is fairly unreactive, just excreting that. And so at these clinics or these hospitals, they have calcium EDTA versus sodium EDTA. And so you go, what's the difference? Calcium EDTA versus sodium, aren't they the same thing? Which one do you think, okay, it turns out one is aggressive, the other is not as aggressive. And so which one do you think is aggressive? Yeah, the sodium EDTA should be the aggressive one because that'll free up the EDTA to do its attacking, right? Whereas the calcium, the EDTA will probably get stuck on it more, be less aggressive. So let's read. Did we do this in Chem 1A? No, we didn't do this in Chem 1A. Okay, we'll do it in Chem 1B. I usually do this in Chem 1A when I talk about solubility rules. Because a lot of people say, you know, solubility rules, why do you have to do that? Because you can just Google it. But, you know, you wish some of these nurses would know a little bit about this. But read this case report, Texas, February 2005. 2005, that's only 10 years ago. A girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary BLL of 47 micrograms per deciliter. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood level. A complete blood count, etc. So anyway, on February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. Chelation therapy is EDTA does what, chelation is claw, so EDTA just claws and bites into the lead. That's chelation. Just keep reading this. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Sexamer, an agent primarily used for treatment of lead poisoning. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. So a mistake because you shouldn't give 2-year-old sodium EDTA. Sodium EDTA is when you have acute, very high blood lead levels that can cause some serious problems. But anyway, so it was corrected by the pediatric resident to calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35 p.m., she was administered 200 milligrams of oral Sexamer. Sexamer is similar in ways. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams. So the EDTA is attacking the calcium in the bloodstream, where it's normal would be 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium levels less than 5. Despite repeated doses of calcium chloride, all attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. I mean, between 4 a.m. and 8:12 a.m. You know, this is so hard to read. I mean, only 2 years old. Simple mistake. August 2005, a boy aged 5 years. Same tragic story. It's unbelievable. 53-year-old woman, 2003, Oregon, etc. This isn't even all of them. There's more. So anyway, Center for Disease Control, CDC, recommends that sodium EDTA be taken off the shelf. So that mistake can't be made. Well, that's always depressing. But, you know, it's the same reason, you know. If somebody were to say, heck, you know, I ran out of milk and magnesia, but I have some sodium hydroxide, aren't they the same? You know, magnesium hydroxide, sodium hydroxide, that's close enough. You know, so when I read something like that, calcium EDTA versus sodium EDTA, they're totally different. You know, it's just like you go to the shelf, you read sodium hydroxide versus magnesium hydroxide, totally different. Yeah. But for some people, it doesn't register. You know, it's the same thing. Okay, anyway, the oxide's going to be locked in the lattice here. And so normally when we think about bases attacking water, you know, the oxide's not going to jump out of the lattice. What's going to happen is the water is going to collide with the lattice, and hopefully it collides in the right orientation so we can get reaction here. And so let's say this sp3 lone pair gets pushed into the S, kicks these out like that. What we're doing here is this is called a mechanism. When we have chemical reactions, bonds break and bonds form. And what we often don't see is, you know, which bonds are breaking and how are they breaking and which bonds are forming. This is very important in organic chemistry if you continue to organic chemistry, because organic chemistry, you know, the structure is very important. You know, in biological systems, they have enzymes and this type of stuff that only react if the bonds, you know, or the atoms are in the right position. You know? And so we have things called optical or stereoisomers. Yeah. But you know, how the bonds are breaking, how the bonds are forming are going to tell you a lot about the structure of these things, and people use this for predictions. They'll use MO theory, they'll use valence bond theory to predict these. Because, for example, when you buy Tylenol, or not Tylenol, let's say, if you buy ibuprofen, do you know that tablet you just consumed? Half the ibuprofen in that tablet is wasted. The other half is active.
Yeah.
Now, that's tons of ibuprofen that's completely wasted. If you can just make one optical isomer pure, you would save tremendous amounts of money. You know?
Isn't it the effects of the side effects that come into play are from the other half of the isomer?
Actually, I don't know. I don't know that well enough to say. But maybe, you know, it'd be good not to have to consume that other half, because there could be side effects from that, for sure, depending on what it does, you know, and how it interacts with the body. But, you know, there are consequences to having that. But it's not digestible. You know, it's like wood. You know, wood is made out of sugar. You know that? Wood is a carbohydrate. It's made out of sugar. It's made out of glucose. We eat glucose, but it would be like eating sugar with half wood chips and half sugar. You know, wood chips, hopefully they just pass through without, but they're going to have side effects for sure. Well, anyway, this is why I'm trying to, you know, it's not that we need to know sp3, sp2, this type of stuff, but in the gap between Chem 1A and organic, it's good if you hear it, you know, a couple of times so you don't forget it when you get to organic, you know. But we aren't going to do that much because we aren't going to get that deep into it.
So you don't need to know SP3, SP2?
No, you don't need to know that to get an A in Chem 1B, you know. It's not that. So if you didn't cover it in Chem 1A, it's like, okay, you know, maybe that's going to hurt you, maybe it's not. It's not going to hurt you in 1B, but it'll hurt you later. Okay, that's all. but I'll be happy to go through it if somebody wants to go through it, do this. The reason is there's going to be a long gap here between, again, 1A and 7A, and something you don't want to forget. That's important. But after I talk about Lewis acids and bases, we really aren't going to talk about it much, because in the next chapter, we're dealing with Lewis acids and bases, but valence bond theory fails. And so all this sp3 junk we don't even use for the next chapter, because you have to use, if valence bond theory fails, you must use molecular orbital theory. Okay. Anyway, so without all the orbital, we just say this lone pair gets pushed onto the hydrogen, because this is negative charge, this is delta positive, pushes these electrons out. So I'm going to avoid saying that. And so what forms? What forms is now hydroxide. And a hydroxide. Now remind me, is calcium hydroxide soluble or insoluble?
Slightly so.
It is soluble. And so what happens is this hydroxide isn't held on as tightly in the lattice as a oxide. Why would a hydroxide not be held as tightly in the lattice as an oxide? Why is this easier to break off a hydroxide than an oxide? Well, you learned this is not soluble, that's soluble, but why would you think? This is just to try to think. The bond is weaker. Why would the bond be weaker?
It's spread between the hydrogen and the calcium, not just the calcium.
It's not double bond, it's single bond.
Well, this hydrogen is oversized. Actually, hydrogens are tiny, and they're going to be stuck on the oxygen. If you look at this as a space filling model, those balls, the hydrogens is a tiny blip on the oxygen. It's not tiny, it's just a little blip on the oxygen, a little bump on the oxygen. Sizes aren't that dramatically different. It's the charge, right? This is only a negative charge. This is a negative 2 charge. According to Coulomb's law, this bond is twice as strong, given the distance is the same, right? All right. And so what's going to happen is we're going to convert all the oxides into hydroxides, and the lattice is going to break apart. Well, now, is there a driving force for something like this? Yeah, I would say there's a driving force because, oxide is a more powerful base, hydroxide is a weaker base. So here, that's our driving force. And so we learn in Chem 1A that metal oxides are basic, because when you react them with water, they're going to form hydroxide. And so anyway, Lewis acid-base reactions are a bit more complicated because, there's not a simple table ranking acids. What's the strongest Bronsted acid? Oh, perchlorate. What's the weakest? What's the strongest Bronsted base? That's easy, you just look it up on the table. What's the strongest Lewis acid? Did somebody in this class ask me if HCl can act as a base? Or was it the other class? Yeah, okay. Somebody asked me about that. It's an interesting thing that you asked me because, when we're thinking about strength, HCl, you gotta be joking me, that's not a base. In fact, I tell my Chem 1A students, chloride is such a weak base, it's neutral. Chloride, I always say this, if you ran out of antacid, can you use sodium chloride instead to neutralize your stomach acid? Will that work? The reason I asked that is because chloride appears on the base chart as a base. But if you read the footnotes there, it'll tell you that chloride is so weak, it's neutral, right? But that chloride is neutral as a Bronsted base. Chloride is not neutral as a Lewis base. And so the question was asked, this acts not as an acid, this acts not as an acid, and gold definitely isn't an acid, right? And so when we look at this reaction, this is a very famous reaction. You guys remember the name of this reaction? The aqua regia. Aqua regia, royal water dissolves gold. What are the chemicals acting as? This one is acting as what we call an oxidizer. This is our oxidizing agent. In fact, nitric acid is one of the classic oxidizing acids. It's called an oxidizing acid versus HCl. HCl isn't necessarily called an oxidizing acid. HCl is called a mineral acid. What's the difference? Both of these are oxidizers. HCl oxidizes things too. HCl eats up metals, right? The difference is in a mineral acid, H plus is the oxidizer. In an oxidizing acid, what's the oxidizer?
The nitrate.
The nitrate is. Nitrate's a much more powerful oxidizer than H plus. So this is the oxidizer, this is a base, and this is our reducer, and acid. This is a two-step reaction. In step one, we have redox. And in the redox, the gold essentially, the gold solid gets converted into gold 3 plus. Gold 3 plus is totally unstable. And so gold 3 plus gets attacked by the base. And so this becomes our acid here. And our base is chloride. The base attacks this and it forms a complex, which we'll talk about, with excess chloride. And so the HCl is just to provide the chloride, which acts as the base. And chloride is an okay Lewis base. It's not the greatest, but it's okay. And so this second reaction is a Lewis acid base reaction. This is aqua regia. And so let's these types of complex Lewis acid base reactions we're going to talk in chapter 24. And so that's why I didn't talk about them yet. And so I'm going to leave Lewis acids and bases, but we're going to return to them shortly. I'm going to leave them for a little bit and talk about redox reactions next. So let's talk about the redox. Okay. Let's see. For redox reactions, most Chem 1A and Chem 4 will do single replacements. But how many single replacement patterns have you memorized? How many different single replacement patterns have you memorized? One? One's not enough. At least two, you should know. Right? But even if you memorize the two main ones, there's still exceptions. And so single replacement works quite well if you're never given an exception, If you're always given something that works, it's going to work. But by Chem 1B, there are too many exceptions, so I don't even bother with single replacement. And so on Chem 1A, I stopped doing single replacements, even though it's the quickest. And I've replaced it with a more general method. Combustion we still use, Combustion we look for things that burn,
Like something that's coming out of their combustion.
Yeah. that something's methane. The methane is what we call electron rich. You know, when I look at the oxidation states, carbon's -4. That's very rich electrons, right? Electron rich, and so I just need an oxidizer. Do things have to burn with oxygen? Can I burn things in the absence of oxygen?
Yes,
Yes.
lithium, like, like I learned what yesterday called electrical fire. So the lithium, when it burns, it doesn't need oxygen.
Yeah, lithium will burn in water.
You can't extinguish that fire with water.
Right. The people there's a battery factory, metal fires, you're never supposed to use water because metals are powerful reducing agents, and water is a very weak oxidizer, but it's an oxidizer. And so if you're trying to put out a lithium fire using water, you're just giving an oxidizer. You're just fanning the flames, right? And so there's a plant, I heard in Japan, a battery plant that was burnt down completely. Not only are you not supposed to use water in a metal fire, but you're also not supposed to use what type of fire extinguisher in a metal fire?
Probably carbon dioxide.
Carbon dioxide. You never want to use a CO2 extinguisher. Why? In a metal fire. Because CO2, if methane is electron rich, CO2 is electron poor. And so you have a carbon in -4 and a carbon in +4. What do you think they're going to do? They react together. Well, in this case, there's not much that's going to happen. Actually, you could use a CO2 extinguisher in a methane fire because the driving force isn't so great. But if you have something even more electron rich, like sodium or lithium, let's go with sodium. How is sodium more electron rich? It's 0. But it is, because we know from sodium is very electron rich. And so here, if you use sodium and CO2, there's going to be even magnesium. Actually, I wanted to show the video, but the video is not working. Maybe it's probably on YouTube. Let me just show you. Have you seen magnesium burn in CO2? No? Let's do that.
On a big branch.
Navigation's officer. What we have here is a block of carbon dioxide, as I say, transport carbons, and into it we place some manganese metal. And we possibly see manganese metal burn in terms of a little manganese ribbon. And we're going to start it off with a manganese ribbon and see what happens. And we're going to well, that's burning nicely now. We're covering it in carbon dioxide.
This test must have a bunch of pits all over it.
Yeah.
It doesn't have very much coverage.
And it's continuing to burn.
I wouldn't want to be in the first row.
Yeah, right. But it's very hot, so it's becoming vapor. You can see the steam coming out. There's no oxygen left in there. It's burning in carbon dioxide. And this is one of the problems with metal fires. If you have a fire that is really metals to burn, as we did there with magnesium, it takes some time sort of difficulty to do it. But once you've got it burning, then it's very difficult to stop it. Putting carbon dioxide on as a fire extinguisher would work, because it actually burns with carbon dioxide.
So CO2, well, CO2 is quite reactive, right? It's an oxidizer. It's acid. It doesn't really participate in metathesis reactions. Well, anyway, that reaction is magnesium solid, and we don't need any oxygen to burn it. We could just burn it in CO2. What do you think the products of this are? Probably magnesium oxide and it could be carbon monoxide, or it could be, actually, I know what the product is. It depends on the conditions. It's like, for example, when you burn methane, it depends on the conditions. You might get some carbon monoxide. You could also get some soot. Soot's a black powder. It's consisting of carbon. And so this is what it forms. We get a lot of soot here. And so after they lift off the other block, I wish they showed it, but the inside will be just lots of black soot everywhere. But the same thing with methane, you don't need, you need something more powerful than CO2. CO2 is not really going to support combustion of methane. You need a more powerful oxidizer. And so there are more powerful oxidizers like fluorine. If we burn methane in fluorine, why fluorine? What's special about fluorine? What's special about fluorine is going to be the strongest oxidizer on our chart. And so this is not going to form carbon dioxide and water. This is going to form carbon with fluoride. How many fluorides can I attach to the carbon? It's going to form carbon tetrafluoride, good, which happens to be a gas. And not water, but H. Not H2. H2 is a powerful reducer. H2 with fluorine. HF gas. Hydrogen fluoride is bad. Hydrogen fluoride is bad. But this is so yeah. You did combustion reactions in Chem 1A, but in Chem 1B, I don't know if I'll throw in a twist like this, But, see if you could figure out if we burned it in fluorine, if we burned it in chlorine. If you burned it in chlorine, what do you expect? HCl and C carbon tetrachloride, CCl4, something like that. This is just pattern recognition, right? And so I think one of the homework problems in Chem 1A, I don't think I assigned it last year, but they ask if you burn it in fluorine, what are the products? Maybe it's Chem 1B, I can't. But that's a homework problem with Petrucci. Anyway, so combustion's just like this, but it doesn't always form CO2 and water. It's going to form CO2 and water if you burn hydrocarbons and carbohydrates. But what if you burn a thiol, something that contains sulfur? If you have sulfur in there, what do you think the sulfur would get oxidized to if you burned it in oxygen? Probably sulfur dioxide, If it's a nitrogen containing, an amine, what do you think you might form? You would form NOx. Have you heard of NOx? NOx are oxides of nitrogen. And there are a whole bunch of NOx. There's this one, nitrous oxide. There's this one, nitric oxide. There's this one, nitrogen dioxide. Which one do you get? Well, it depends on the conditions that you burn it, right? Just like we don't know, are we going to get soot? Are we going to get carbon monoxide? Are we going to get carbon dioxide? Well, it depends on how you burn it, right? The conditions.
When you get a little bit the other, other possible.
Yeah, there must be limited amounts, right?
Other possible what?
If, for example, you said that it depends on the condition.
Yeah.
But regardless of the condition, wouldn't you also get a little bit
A mix.
of the other?
Yeah, you get a mix, right? And so this is why we call it NOx. We get a mixture of these, usually. We don't get one, unless you go all the way. If you burn this all the way, you should end up with, this is what we call complete combustion, NO2. When you do complete combustion of hydrocarbons, you'd get CO2. You wouldn't worry about the soot. You wouldn't worry about the carbon monoxide. You go all the way. Well, that's what we're going to do in our predictions. We're just going to go all the way, complete combustion, right? Do you have a question? No. There could be little twists there. How do you know about these little twists? If you read every single problem, you'd see the problem like this, and then you go, oh yeah, I've seen that before. You know, it's okay because again, you're learning by example here, and so the more examples you see, right, the more you learn. Chart method is this chart method is, for lack of a better name, this is what I call it. But it's just a method that people use. It doesn't have a formal name. If you want some additional info on this, it can be found in the electrochemistry chapter. But they don't do it to predict the reactions. They do it to build batteries. And so I don't want to deal with batteries right now. I just want to use the chart method. We have things called potential diagrams. Potential diagrams tell us, when there are a mixture of things possible, what should be most likely thermodynamically. And then we have skeleton redox. Skeleton redox is something that you do in Chem 4, Chem 1A. It's where you split things into half reactions and balance the oxygens, the hydrogens, the electrons, right? That kind of thing. So I did a little bit of talk about the combustion. That's it. You just might see more exotic oxidizers, like CO2, whatever. Again, I told you I'm going to skip single replacement. We don't need single replacement if we use this method. This method is exactly the same almost as the Bronsted method. So, oops. What we do here is we inventory the species present, and then we find the strongest oxidizer present. The way we find the strongest oxidizer present is we use a chart like this. A chart like this lists the oxidizers on the left, the reducers on the right. But look, the strongest oxidizer is fluorine. The weakest oxidizer, and this chart's very tricky. A lot of people in the final exam ask me what's going on because they never looked at it during the semester. But make sure you look at this and figure out what's going on with this little subtable here. Is the weakest lithium ion here or water? It's lithium ion. There's a conjugate relationship between oxidizers and reducers. Just like there's a conjugate relationship between acids and bases. So let's plug this in. The strongest acid will have the weakest conjugate base. The strongest oxidizer will have the weakest conjugate reducer, which makes sense. Because the strongest oxidizer, what do oxidizers want to do? Oxidizers want to gain electrons, right? This is back in chapter 5. Well, if oxidizers really want to gain electrons, then they don't want to lose them once they're gained. And so fluoride, the conjugate, would be an extremely poor reducers because reducers lose electrons. And so a powerful oxidizer gives a very weak conjugate reducer. A very weak reducer gives a very powerful conjugate oxidizer. These are conjugate pairs. So we only need one table. Problem is this one table is not always consistent. Acid base is pretty consistent. The acids are always on the left, the conjugate bases are on the right, right? These tables are mixed up. The reason these tables are mixed up is because of the activity series. You guys remember the activity series? At the top of the activity series is lithium, then potassium, calcium, sodium. This is an inverted activity series. And so some people like the activity series. And so what they'll do is they'll flip this table and then take the mirror image. And so when they do that, then lithium ends up at the top left. And they put all the reducers on the left and the oxidizers on the right. And so you see this table isn't always consistent. And so this is why you always remember two things. You remember fluorine and lithium. And so it doesn't matter what the orientation is, you can always reorient yourself. Like if you're in space and you have no landmark, then you can always orient it. Just like a table like this. So we always remember those. A lot of people, again, you know, there's a lot of entries here. You don't memorize this, but you look for patterns. And not only that, when you're looking for patterns, the first thing is you just read them. Fluorine, ozone with acid. You know, I don't know what the name of this is. S2O8, 2 minus. But you know, it looks like a bisulfate or persulfate or something like that. But this is a very weird ion. This is a very weird ion. This is something you do when you have time. You know, is you go, why is that way up there? Where's sulfate? I don't even say, well, sulfate's way down here. This is way up there. Sulfate's way down here. This is way up there. What's the difference? This looks like 2 sulfates put together. But I'll tell you why this is weird. This is weird because look at the oxidation states. What goes first? Sulfur or oxygen? Oxygen -2. That means sulfur is, if oxygen is -2, that's -16. -16 plus 2 times what will give you -2? Is it +7?
7.
It's got to be +7. That's +14, -8, 16. Oh, that's right, -2. So each one's +7. What's weird about having sulfur in a +7 oxidation state? Huh? Oh, it's totally unstable. Why? Yeah, what do we call that? When you take more than its outer shell. Like carbon. This is what we call the range for carbon. Do you know the range of oxidation states for carbon? Carbon, what's the biggest negative oxidation state and what's the biggest positive oxidation state? What's the positive and negative range of oxidation states for carbon? +4 to -4, right? +4, because if it loses 4, then it's lost all its valence electrons. -4, because if it gains 4, then it's filled its valence shell. That's the range, the normal range. What's unusual about having sulfur +7? What's the normal range of sulfur? Tell me the normal range of oxidation states for sulfur. It goes from plus what to minus what? Sulfur ranges from plus not +2. Okay, well, okay, it ranges from -2. -2 would fill its shell. To +6. Because +6, it'd lose all its valence electrons, right? This is sulfur +7, which means what happened? It lost 1 core electron. Yeah, it lost 1 core electron. If you guys remember ionization energies, losing a core electron, is it twice as much energy to lose a core electron versus valence electron? 10 times as much energy, or 100 times as much energy? Or even 1,000 times as much energy? If you looked at the numbers, you can make a generalization. If you look at the numbers, we can make a generalization. Take a look at the numbers again and generalize it. This is why I say don't memorize the numbers, memorize the pattern. If you know the pattern, then you know the answer to this. You know what? When I was a student, one of my professors told me, you know, make sure you read the tables carefully. In his experience, most students don't. So I started reading them carefully. Didn't it, you know, that just meant reading the footnotes. A lot of people skip that. Then I started looking at them even more carefully because I wanted to see if I recognized any patterns. You know, because that's all I ever did. Being, you know, working in science, working in research lab, that's all you ever do is look for patterns. Look for patterns. Hopefully that correlates with something. That's called data reduction. You're taking a whole jumble spaghetti stuff and hopefully reducing it into some simple patterns. But, well, you know, it's about 10 times more difficult. Costs 10 times more energy. And so typical ionized, let's say it's 2,000 kilojoules to ionize the valence, but it'll be like 10,000 kilojoules or something. Ionize a core. It can happen, right? You know, when I was an undergrad, I was trying to make iron 4 iron plus 4. Have you heard of iron plus 4? No, you haven't heard of iron plus 4 because iron comes in plus 2 and plus 3. I was trying to make plus 4 iron. Some people claimed to have made it iron plus 4 in this compound, so I just wanted to reproduce what they did. And so I needed a powerful oxidizer to do that. So I used a powerful oxidizer. Although fluorine's not the most powerful oxidizer, it's one of the most powerful oxidizers out there. And so that.
How about manganese?
How about what? Permanganate?
Yes.
Permanganate is on this chart, right there. What's its ranking? Its ranking is 1, 2, 3, 4, 5th on the chart. Permanganate's very powerful, though. One of the few explosions that I had in Chem 1B was due to permanganate. Was it? Yeah, it was due. I think it was due to permanganate. This person was actually. This is our first lab is going to involve a synthesis. We're going to use ethanol in our synthesis. Ethanol is a. Is it flammable? Yes. Ethanol is a great producer. Whereas this person was late making up a lab. This is why sometimes I don't like make-up labs. And I said, okay, you can make up this lab. The person was using ethanol. So I said, the ethanol waste goes in this waste jug. Everybody else is doing this experiment with permanganate and some other powerful oxidizers. That waste goes into this waste jug. The person, in their rush to get the experiment done, poured the ethanol into the wrong waste jug. I didn't think that was going to happen because I explained to them, don't do that. And an explosion resulted. The waste jug exploded. The waste jug didn't shatter because the waste jug was open, but just a huge fireball came out, and there was a big bang. And they're kind of short, so their face was inside there, and their face got burnt from that. Yeah, their hair. Fortunately, they weren't severely injured, but the injuries did result. And so then I thought, boy, this is Chem 1B. Chem 1B, they should know. You know, those are incompatible chemicals. And so and then I thought, you know, maybe I'm emphasizing too much physics and not enough chemistry. And so even though this is a repeat for you guys in Chem 1A, do it again. Because we're doing some dangerous reactions this semester. I don't want any accidents to occur by mixing the wrong things.
Wait, but when we use ethanol, we still have to turn on the Bunsen burner. So how can we not get ethanol to get that Bunsen burner thing?
Don't turn on the Bunsen burner, please. We have hot plates. We use hot plates. But when you use the ethanol, you're going to use it in an ice bath. And so we don't want any heat when we use our ethanol. We want cold. And so you don't have to worry about Bunsen burner. But the thing is, this also happens. If somebody is using ethanol, don't light a Bunsen burner, please. I'll bring in an ethanol rocket. Also, you know, especially ether. You know, I heard a story last semester. People were using ether and somebody lit the Bunsen burner. You would never do that in ether fire. Because ether vapors are more dense than air, so they sink to the bottom, so the fire burns from your feet up and causes a lot of deaths, ether fires.
And then when that happens, you have to drive someone to the safety shower right away.
Yeah, right. If you see somebody on fire, for sure. But if you don't have time, we have safety showers at each sink. You just pull the hose and then douse out the flames. That would be better. Because in the time it takes you to go to this safety shower, damage has been done. You know, you need to get that. Or, you know, and this goes for everybody. If you see somebody doing something unsafe, or if somebody needs help, you got to help them, right? This happened, you know, at UCLA, there was that big fire, and so safeties. Did you hear about that? Well, a lot of these things, do you think you need a match to do this? For example, do I have to worry about a fire right now? No. Ooh, it smells bad. It smells bad because the methane smells bad, or they put some odor into it. They put sulfur-containing organic compounds to stink it up, I think, right? So it stinks bad. I think we need a break times. But some combustion reactions require no match. Immediately, when this comes into contact with air, it ignites. Those materials are called pyrophoric. Those are when you get some powerful reducers. Oxygen will just ignite it right away. Well, let's take a break here a little bit, and then we'll just